Hello, my name is Harry Chen, and I will be covering abusing integral bounds. This is going to be a shorter lecture-style video, so we are going to go over 3 integrals which use this trick. So first, we have this monstrosity of an integral. The integral from 1 to e of e minus 1 times the square root of 2 arcsines of the natural log of x, all divided by pi, plus 1, plus exp just means e to the power of, so e to the power of sine of pi times the quantity x minus 1 all over e minus 1 times square root of 2, all squared. So this seems super ugly at first, and I really don't advise you to do this term by term. Instead, we are going to abuse the problem. So the first thing to notice is that this function here and this function here are actually inverses. You can verify that yourself. I'm not going to go over why, but you just set y equal to the thing and then solve for x, and then you should get that they are inverses. So let's let this one here equal f of x. So let's try graphing this. When you graph it, it looks something like this. So this is f of x. So, and this is 1 to e. And so you can see it's an increasing function along this interval because the inside here is increasing, sine keeps it increasing. Since this term here is all between 0 and pi over 2, this whole thing is increasing as well. Oops, that went over. So the sine is increasing, and then exponentiation preserves increasing this, so the whole thing is increasing. The important thing to notice is that since this part is the inverse, so this is the inverse of x. Well, first of all, we notice that over here, this is at y value equals 1, and this is actually at y value equal to e. Yeah, this can be verified by just plugging them in. And so it turns out that the integral of this term here is as this shaded area, the black shaded area, and the integral of this term up here is actually the red shaded area. And so what does that tell us? Well, that tells us that we can actually just take this whole square here and subtract this small square from that. And so that's actually just e squared minus 1 squared. So this is just actually equal to e squared minus 1. This would not be possible if it was not bounded from 1 to e. So, yeah. This is a second example. It's a little bit cleaner than the previous one. So here we're actually going to be using u sub. But before we do that, let's try u sub. So the most obvious thing would be u is equal to cosine of x. The only issue with this is that it does get rid of the sine of x, but the x at the top doesn't get sense. You get something along the lines of inverse cosine of x all over 1 plus x squared, and this just isn't really nicer in many ways. And so we're actually just going to skip. We're not actually going to use that right now. So the trick here is let's first let I equal this whole integral. So I is some constant value, and so we want to make a u sub, and the trick is that we actually want to make sure the bounds stay the same, but the inside here, the integrand, changes into something that we can actually use. And so what u sub might preserve the bounds? And that u sub would actually be u is equal to pi minus x. We get du is equal to negative dx. And so when we plug this in, this is equal to the integral, negative integral from pi to 0, because pi minus 0 is pi minus pi is 0, so that's where we get the bottom and top. And then pi minus x sine of x over 1 plus cosine of x squared. The reason the sine x and the cosine squared of x don't change is because sine of pi minus x is still equal to sine of x, so that we can just simplify, so that stays the same. And then cosine of pi minus x is actually equal to negative cosine of x. But since we square it, the negative doesn't matter, so it stays cosine squared of x. And so this is yes, dx. So we have a negative in front of the integral, and these bounds are the same bounds as up here, only switched. And so we can actually, using properties, we can actually get rid of the negative and then switch the bounds. So this is actually equal to the bounds can actually be turned into 0 to pi again. And this is incredibly useful because now integrals are additive, so we can actually add the top equation and the bottom equation together. So we get that 2i is equal to the integral from 0 to pi of, it turns out it actually just simplifies to pi sines of x over 1 plus cosine squared of x dx. The reason for this is because the negative x sine of x over here and the x sine of x cancel out, so we're just left with pi times sine of x. And over here now we can make a u sub, let u equal, let u is equal to, cosine of x. So du is equal to negative sine of x dx, and so from here the rest is pretty easy. So we get 2i is equal to negative integral from 1 to negative 1 of pi over 1 plus tangent squared. That's not t. Wait, not 1 plus tangent squared. Sorry, just 1 was 1 plus x squared. Or sorry, u squared. Sorry, u. Oh yeah, I should probably explain up here. Up here, I put x's here. Technically, you're putting u's here, but it actually doesn't really matter whether it's x's or u's, as long as it's all the same thing. So because you know, the x or the u or whatever symbol you use to represent whatever is in the integrand is just it's just a symbol, basically, you could say. So I kind of skipped a step between the first line and the second line, and that's that you turn the x's back into u's. Anyway, so we have integral from 1 to negative 1 of pi over 1 plus u squared. This is equal to is equal to pi times negative inverse tangents of u, evaluated from 1 to negative 1. And so this is actually equal to pi squared over 2, I think, if I didn't make any algebraic errors. So that was cool. I don't think there's a closed form. Like, I don't think there's a nice indefinite integral for this. So you really have to use the fact that you can preserve the bounds but still make changes to the integrand. Oh yeah, sorry, you have to divide by 2 at the end because it's equal to 2i. So there we go. Pi squared over 4. This one's a slightly harder variant of the one we had before. And so the trick here is, well, the bounds are from 0 to pi over 2, and we have the natural log of sine of x dx. And so similarly to what we did last time, we can let u equal pi over 2 minus x. So du is equal to negative dx. I'll spare you the details and just let me put this as I is equal. I'm going to let this equal I again. So it means this I is still equal to the integral from 0 to pi over 2 of the natural log of cosine of u du. Remember, we can turn the u's into x's if we want, and we will do that. So we can turn the u's into x's, and then when we add these together, so we get 2i is equal to integral from 0 to pi over 2. And then when we add up natural log of sine of x plus natural log of cosine of x, we can use integral properties to bring the sine and cosine and multiply them together. So this is actually equal to natural log of sine of x cosine of x dx. And so the reason we want to do this is now that we have sine of x, cosine of x. That's very resemblant of the sine double angle formula. So that's that sine of 2x is equal to 2 sine of x and cosine of x. So this actually simplifies back into power over 2 of natural log of 1/2 sine of 2x dx. Using integral properties, we can actually bring the 1/2 outside. So this is equal to the integral from 0 to pi over 2 of the natural log of sine of 2x plus the natural log of 1/2 dx. This is just a constant, so we actually bring this out, and this particular term turns into natural log of 1/2 times x from 0 to pi over 2. This just becomes pi over 2 natural logs of 1/2. So now we just have to evaluate the rest of this, the natural log of sine of 2x, and we'll do this. So let's go to the next slide. So to do that, we can first make a kind of clever u sub here. So u is equal. We can let u is equal to 2x because right now we have a kind of a pesky 2x inside of the sign, and that's not what we want. So 2i is equal to the integral from 0 to pi times 1/2 of the natural log of sine of x. So this is very resemblant of what we had before. Very resemblant. Oh yeah, plus pi over 2 natural logs of 1/2. And it turns out that sine of x is symmetric. Sine of x is symmetric around pi over 2, so we can actually just split the bound back into 0 over to pi over 2, and then multiply this whole thing by 2 since there are 2. So the easiest way to show this is that well, it's actually just to shift the bounds again. So we can show that with the integral from 0 to pi over 2 of natural log of sine of x dx, if we let u equal pi over 2 minus x, sorry, not pi over 2, just pi over x, then we can show that this whole thing is equal to, this becomes simply pi over 2 to pi of the natural log of sine of x, again, dx. And so if these two are, if this and this are equal, then that means, well, when we add them together, well, that means this is equal to 1/2 of this expression. So we can say that 2i is equal to the integral from 0 to pi over 2 of the natural log of sine of x dx plus pi over 2 natural log of 1/2. Beautiful. And so do you remember what I was? I was literally this integral. So this is just I. So if you subtract I from both sides, you just get that I is equal to pi over 2 natural logs of 1/2. And that is our answer. So we can find that. So yeah, ultimately, abusing integral bounds means that we can find the value of definite integrals without actually having to find an antiderivative directly. So yeah, so this was abusing the integral bounds. Hope you enjoyed.